Okay, so we'll go back to another video. So here we have the limit as n approaches infinity of the nth root of a plus the nth root of b divided by 2 to the power n such that a and b are positive real numbers. So I think this is actually a perfect example of when you're learning calculus when you're dealing with limits of indeterminate form, and this is actually going to be a quick one too, but you can already tell that this is indeterminate form for 1 as n tends to infinity, that we're going to get an indeterminate form of 1 to the power infinity. So with stuff like this, indeterminate forms, you're going to have to get a little creative on a way that if you can rewrite the function itself so that as you take that limit, it does not become an indeterminate form, which we're going to be relying a little bit of algebra. And actually, you'll notice that, I think, spoiler, the first thing we're going to do is actually we're going to take the natural log of both sides because we have that the power n over here is actually a bit of an obstacle. So that's one way to take to that approach. So this is going to be a quick one. I think this is actually a good one. So let's actually just jump right in. So I'm going to call this L. So L is our same limit as n approaches infinity of the same thing of our given. So now if I were to take the natural log of both sides, so I have ln of n, so that means the n will come outside, and with continuity I'll put that as the limit as n approaches infinity of n times ln of the square root of a, or rather the nth root of a plus the nth root of b, and then divided by 2. So you'll notice that if I were to take this as n approaches infinity, we're actually going to get yet a indeterminate form of infinity times 0. So this is actually a big no that you should not do and write as your answer. If you're trying to evaluate this, you have to keep going on how we have to convert this so that it's not an indeterminate form. No worries, we can fix this up such that, because this whole thing is not in a rational form, we can fix that up such that n can be rewritten as 1 divided by n under the denominator. And so, written as so, we have that the limit as n approaches infinity of our numerator, so ln of the nth root of a, add this with the nth root of b divided by 2, and then under our denominator we have 1 divided by n. So if I were to take this as n approaches infinity, so we're going to have 1 plus 1, 2 divided by 2 is 1, so ln 1 is 0, and we have on the bottom this is 0 again, so that means we have yet a 0 over 0 indeterminate form. But what's great that this is a rational function, so we can actually apply L'Hopital's theorem to actually take the derivative of the numerator and the derivative of the denominator, and once we get that, we'll see that if we actually take n approaches infinity such that if it does approach to a value, then we're pretty much done. But if it does approach some indeterminate form, we're going to have to keep going to reconvert it. So what we'll have to do is, again, as mentioned, take the derivative of the numerator. So let's actually take this one step at a time. So let's calculate, or let's rather take the derivative of our numerator in respect to n. So in respect to n, so I have ln, and then the same thing over here, nth root of a plus the nth root of b, and then divided by 2. So what would that derivative look like? So I'll put this on the next line. Okay, so we know that the derivative of the natural log, so it's basically just 1 divided by whatever in the argument, then you take the derivative. So now in this case, I'll write this as 2, and I'm going to write that exponent for the nth root of a as the following. So I'll write this as a to the power 1 divided by n, and then add this with b to the power 1 divided by n. And so now let's take our derivative of what's inside the parentheses. So I can, for one, just factor out the 1/2, and then we just have to take the derivative of the nth root of a plus the nth root of b. So in other words, we have that it's a constant raised to some variable derivative. So in other words, in that general base form, we have that this is going to be equal to negative a to the power 1 divided by n, and then ln of a, and then you have to take the derivative of the exponent over here. So 1 divided by n, its derivative is negative 1 divided by n squared. I know I wrote the negative a little early, but that's where that comes in handy. So basically, and that's the same thing for the nth root of b, just do the same thing. So it's negative, and then b to the power 1 divided by n, ln of b, and then divided by n squared. So there's some things that we can simplify out. So let me actually move on to this line. For one, the 2's will cancel, and then another thing is that I can factor out a negative 1n squared from over here. So yielding us is that we have 1 divided by a to the power 1 divided by n plus b to the power 1 divided by n, multiply with negative 1 divided by n squared, and then leave this out with a to the 1 divided by n ln of a, add this with b to the power 1 divided by n ln of b. Okay, and the straightforward, we know the derivative of 1 over n is negative 1n squared. So nicely done that I can actually now substitute everything back that are separate derivative calculations we did. So yielding us that we have negative 1 divided by n squared on the numerator, well, and then now plus or times 1 divided by 1 over n plus b to the power 1 divided by n, multiply, and then with over here a to the power 1 divided by n, ln of a, add this with b, 1 to the power n times ln of b. So that's good for our numerator. And then our denominator, again, it's the derivative as mentioned, that's negative 1 divided by n squared. Nicely done, that you'll see that we have some things that cancel. We have the negative 1 divided by n squared cancel from both the numerator and denominator, and we're just left with what's left of the 1 over an and then the composition together. So yielding us now that so far, I'll reiterate and say that ln of L so far is that we have the limit as n approaches infinity of a to the power 1 divided by n, ln of a, add this with b to the power 1 divided by n, ln of b, all this divided by a to the power 1 divided by n plus b to the power 1 divided by n. Now, this is nice that if I take n approaches infinity, a, and then this is going to approach 0, so a to the 0 is going to be 1. So I have 1 here, so that means this is just going to be 2 on the bottom, and then that's going to be just ln of a plus ln of b divided by 2. And so therefore just take e base to the both sides, so we're left with L, which is what we want to evaluate this limit to begin with, is that this is the same thing as, and also just to take one step further ahead before I move to the next line, is that I can use natural log property to say this is ln of a times b divided by 2. Okay, so e base both sides, so it's 1/2, and then ln of a to the b, that's a constant outside the natural log. I'll move this back inside, that's the square root. So in other words, L is indeed just equal to the natural log of the square root of a times b, which is finally our closed form for this limit given for both a and b being positive real numbers, just like that. A simple, quick L'Hopital's rule example, just like that. So yeah, that's pretty cool if you ask me.